Hi everyone, my name is Fiman Kate and I am happy to present our work, SmartPhOx, smartphone-based pulse oximetry using a meta region of interest. Since April 2020, the world has been aware of a particular form of pneumonia that leads to what we call silent hypoxia. This is when blood oxygen level drops to very dangerous levels without the patient realizing it. While normal SpO2 is between 95 and 100% and below 92% is already a dangerous situation. We have seen cases where patients arrived at the hospital with SpO2 as low as 50%, having felt nothing until then. This is what motivates the idea of making it possible to regularly monitor one's own oxygen level in daily life. But in concrete terms, what solution can make such a vision possible? In one hand, we have medical oximeter that are not very common in our daily lives and that are expensive. On the other hand, there are smart watches and high-end smartphones that have dedicated SpO2 sensors, but they are not really accessible to everyone, especially those in developing countries. As a third option, we can make use of camera and flashlight readily available on standard smartphone to measure blood oxygen level. With a penetration rate of 83% today, it is natural that the smartphone is considered as the best candidate to democratize home self-monitoring of blood oxygen level. In the rest of the presentation, we will start by studying the challenges of measuring blood oxygen level with a smartphone. Afterward, we will present the construction of our solution, SmartPhOx. When a light source, such as smartphone flash, passes through the finger, it is absorbed by all its constituents, such as flesh and blood. The amount of residual light depends on the amount of blood in the finger, which itself varies over time according to the heart rate. This signal is called Photoplatismogram or PPG. The characteristic of this signal depends on the composition of blood and the wavelength of the light source, so that by measuring PPG signal for two different wavelengths, we are able to measure the composition of blood, in particular, the proportional amount of oxygenated blood or blood oxygen level. Mathematically, this is written by an equation of this form with RR calculated from the two PPG. RR is called ratio of ratio. It is the blood oxygen level feature computed from the two wavelength PPG signals. Now with 3 users, we investigate the results of this RR method. The user is asked to sit comfortably with his left middle finger on the smartphone camera, while the index finger is on the oximeter, as shown in the figure. The collected video is then processed to extract the red and green PPG as the two wavelength PPG, and then the corresponding RR over time are computed. While SpO2 was stable at a normal value of 99%, we noticed that the RR is very volatile over time for each user, which makes it extremely challenging to infer blood oxygen level. This is proven by the figure 2, the second figure, where we converted this RR into blood oxygen level with a pre-established model. We can see that the absolute error can go up to 15%, far from the FDR clearance limit, which is 3.5. The challenge of smartphone oximetry can then be reduced to that of obtaining consistent RR. In other words, similar RR for similar blood oxygen levels. One approach that can be used to get consistent RR is to say that if we have a bad RR, it may be because the underlying PPG signal is very noisy. In order to investigate this point, we will consider 2 RR that are quite distant from the previous data, as well as the underlying PPG signals. To evaluate the quality of the PPG signal, we will use the QQ metric introduced in a previous work. It quantifies how well the signal conforms to a sinusoidal signal of the same frequency corresponding to the heartbeat. In other words, the closer to 1 it is, the better the signal quality. We can see that these two air, although so distinct, have signal of highly discernible quality. Indeed, the air producing 5% error has red and green signals with score of 0.95 and 0.94 respectively, while the air producing 0.1% error has a red and green PPG signals with a score of 0.954. This allows us to conclude that the quality of the signal alone does not guarantee the consistency of the air. This is understandable as the calculation of the blood oxygen level require not only the integrity of the shape of the PPG signals, but also the integrity of the relative value of one PPG signal to the other. Remember, it is the ratio of absorption of one wavelength to the other that contains the SpO2 information. A second approach could be to pay attention to the region of the frame from which to extract the signal, also called region of interest. Indeed, as the region of the frame are not subject to the same condition like illumination or movement, one can expect that the result depend in it in some way. This can be seen, for example, in the quality of the signal, which also depends on the region. Let's introduce what we call the air map in order to investigate this point. The input image is divided into cells, and for each cell, PPG signals and air are calculated. The set of all air value of the cells of a particular video input constitute is air map. The air map reveals that each cell produces different air. We can even have air that are 3 times larger than others within the same frame as shown by the color scale. It is also possible for cells to produce similar air, and this can happen whether or not they are neighborhood. Looking at the air map over time, we can also see that air produced by each cell vary over time, even though the SpO2 is stable. However, some cells seem to vary little, as can be seen in this figure illustrating air map at 2 successive time instants. There we see, for example, that cells 1, 9 and 13, 4 vary very little between the 2 instants. The analysis of these air maps highlight the difficulty of using a predeterminate and fixed region of interest to infer the blood oxygen level. Indeed, it seems that each region of the image is likely to produce very volatile air without knowing it in advance. However, it is clear that there are some mutually consistent cells in space and time. This is the basis of SmartPhOx intuition. Indeed, we propose to use the air themselves to directly filter the air in order to provide a robust estimation of blood oxygen level. We will dynamically determine a virtual region of interest composed of cells that are mutually consistent and stable over time, which we will refer to as a meta region of interest. SmartPhOx, our contribution, is therefore a solution for measuring blood oxygen level using a standard smartphone. It is structured around 3 blocks, one related to the hardware that concern mainly the mobile application, the next related to the measurement, and the last to the extraction of the signals and the calculation of blood oxygen level. The first step of SmartPhOx is to record the data. While the user places his finger on the camera, SmartPhOx records the video with the flashlight on. for enough time to be able to calculate several RR and evaluate the temporal consistency. Technically, knowing that the PPG signal of W seconds are needed to calculate a single RR, the recording must last T equals to zeta plus W minus 1, where zeta is the number of RR that will be calculated using the signal in sliding windows of 1 second. Now, once the data has been captured, the algorithm block comes into play. At this stage, the RR map is calculated as described above. With zeta RR and x times y cells, we obtain an RR map of size x times y times zeta. The choice of x, y, and zeta are parameters whose impact will be evaluated. Now the goal is to group the cells that produce similar RR over time. One approach is to consider this as a classical clustering problem. First, let's give a formal definition on what we call space-time consistency. Let S be a clustering of the RR map cells. Two cells are considered consistent in space and time if they belong to the same cluster in S. And the set of cluster in S are referred to as space-time consistent regions. We will use the Davis-Boolean index to determine the optimal clustering. The Davis-Boolean index allows to quantify how distant are clusters of a clustering. Thus, by iterating on K, we will stop when the clustering has the best Davis-Boolean index. Once we have our set of consistent region, the next step is to select the best one as the meta region of interest. For that, it is necessary to define a metric allowing a comparison of these regions. It must satisfy two constraints. The first one allows quantifying the temporal stability of a cluster, as well as the second constraint, which is allow a meaningful comparison between two clusters having RR of different order of magnitude. We will use the coefficient of variation. It is a metric that allows to measure the dispersion of a population. It is also normalized, thus allowing a fair comparison of clusters of different order of magnitude. Now, for a given clustering, the best cluster or the best consistent region is the one with the lowest coefficient of variation. In summary, the meta region of interest algorithm is as follows. From the RR map, iterate over K and apply the K-mean to the RR map. Calculate the Davis-Boolean index of the clustering, and if it is minimum, calculate the coefficient of variation of each cluster and retain as meta region of interest the one with the lowest coefficient of variation. In order to evaluate the performance of SmartPhOx, we conducted a data collection campaign with 37 users of different age and skin color. We compare SmartPhOx with different region of interest selection strategies used in the state of the art. Full frame, which consists of extracting PPG signals by combining all pixels in the frame. Central region of interest, which consists of extracting the signal from a fixed central area of the image. The idea being that in the center of the image, the lining is more stable and then result may be more stable. Max AC, which consists in using as a region of interest the cell producing the signal with the highest oscillation amplitude across the frame. The idea this time is that the pulsatile part of the signal being directly related to the cardiac activity can be a good proxy for signal quality. For each strategy, we use leave one out cross validation to train the regression model, validate it, and test it. This figure shows the root mean square error of the different approaches. The data shows that SmartPhOx perform better than all other approaches. SmartPhOx has a root mean square error of 3.04%, while the second best is 3.77. Most important, SmartPhOx is the only approach to meet Food and Drug Administration root mean square error requirement for pulse oximetry. We conducted a one-tailed t-test on SmartPhOx prediction error. In particular, the statistical test is aimed at answering the question of whether SmartPhOx prediction error is on average lower than a given value, x. Toward this, we performed a one-tailed t-test over the set of SmartPhOx prediction error for various values of x. The data shows that the probability of SmartPhOx average error being above a given x drops below 0.05 for x equals to 2.39% and below 0.005 for x equal to 2.43%. We then compare SmartPhOx to a complete state-of-the-art solution, Pho2. We see that the 80th percentile of SmartPhOx is quite close to that of Pho2, which is 3.5%, while SmartPhOx is at 3.83%. This suggests that the SmartPhOx approach avoids the need for custom hardware add-on. This figure shows the importance of temporal stability, which is represented by the zeta dimension. It can be seen that for zeta equals to 1, for example, the error is more than 4%. This is because the selected consistent region is certainly a stable region in space, but not necessarily in time. Then, as zeta increases, the performance improves since the time consistency is taken into account. From zeta equals to 6 onward, however, we notice that the performance stopped increasing significantly. Regarding the number of cells, we vary x times y from 5 times 5 to 40 times 40. This corresponds to 256 times 144 pixels to 32 times 18 pixels. We can notice that the root mean square error of SmartPhOx is decreasing with the sharpness of the frame division. Indeed, when the cells are too big, it is difficult to identify a consistent meta region of interest. However, we notice that from a cell size of 96 times 54 pixels, which correspond to x and y equals to 14, the root mean square error falls below the FDA limit. This explains why we retained as default parameter x equal to 14 and y equal to 14 and zeta equal to 6. We are now interested in the robustness of SmartPhOx to the experimental condition. First, we vary the finger from which measurements are taken. The result shows that taking measurement on the middle ring or little finger does not significantly change the distribution of the error of SmartPhOx. Secondly, we evaluate the impact of the ambient light on the performance of SmartPhOx. To do so, we take measurement in a completely dark room. We then try to predict the blood oxygen level first with a model trained with data taken in ambient light, then with a model trained with data taken in a dark room. This image shows that the error distribution are quite similar with and without light. It also shows that in complete darkness, we have slightly better performance when we train the model with the data of dark room. As a conclusion, we can say that we presented SmartPhOx, the first pure camera and flashlight smartphone-based pulse oximetry solution to meet FDA root mean square error requirement. We introduced the concept of meta region of interest, essentially using the signal as a filter to itself. We implemented as an Android application our solution and evaluated it using 37 volunteers. As future work, we plan to extend the evaluation to non-healthy subjects, ideally COVID-19 patients. We also plan to extend the blood oxygen level range to 70 to 100%. Another relevant point can be make it purely passive by using the front camera. Thank you for your attention. I will be happy to answer your questions.